Hello, this is Professor Kuehn. Let's pick up where we left off in looking at James Clerk Maxwell's On Action at a Distance from 1873. You might remember that we were just discussing the work of Isaac Newton as recounted by Maxwell. Maxwell was pointing out that Isaac Newton, when he came up with his universal law of gravitation, considered this to be a mediated action, even though he was not sure what the medium might be that would communicate this action. But the people who promulgated Newton's works, most notably Roger Coates and Father Boscovich, advocated immediate action, that is, action at a distance. So we're picking up on page 385 in A Student's Guide to the Great Physics texts. He says, but if we leave out of account for the present the development of ideas of science and confine our attention to extensions of boundaries, we shall see that it was most essential that Newton's method should be extended to every branch of science to which it was applicable, that we should investigate the forces with which bodies act on each other in the first place before attempting to explain how that force is transmitted. No men could be better fitted to apply themselves exclusively to the first part of the problem than to those who considered the second part quite unnecessary. So for those of you who have studied a little bit of Isaac Newton, his Principia, in my Physics 151 or 201 class, you might recall that in one of his scholia, he talks about his methodology, how the first thing one should do is try to understand how nature behaves and what the laws governing nature are, and then to speculate about the reasons why they might be behaving that way. So that is exactly what Maxwell is pointing out here. There are a number of scientists who are very interested in studying how nature behaves, coming up with precise mathematical formulas, and he's going to talk about specifically the French scientists of the 18th and 19th century. And notably, many of these scientists did not believe that the second part of the problem, that is explaining why it behaves in that way, was even a scientific question at all. They were strictly interested in a mathematical description of nature. He says, accordingly, Cavendish, Coulomb, Poisson, the founders of the exact sciences of electricity and magnetism, paid no regard to those old notions of magnetic effluvia and electric atmospheres which had been put forth in the previous century, but turned their undivided attention to the determination of the law of force, according to which electrified and magnetized bodies attract or repel each other. In this way, the true laws of these actions were discovered, and this was done by men who never doubted that the action took place at a distance, without the intervention of any medium, and who would have regarded the discovery of such a medium as complicating, rather than as explaining the undoubted phenomena of attraction. We have now arrived at the great discovery of Ørsted, of the connection between electricity and magnetism. Ørsted found that an electric current acts on a magnetic pole, but that it neither attracts it nor repels it, but causes it to move around the current. He expressed this by saying that the electric conflict acts in a revolving manner. So you might remember back to the beginning of the semester when we were studying the work of Hans Christian Ørsted, the Danish scientist who discovered that when you pass an electric current through a wire, the magnetic compass needle points in a direction around that wire. And Ørsted speculated that there was some kind of, he called it electric conflict, some medium swirling around the wire that helped direct the compass needle. So this was a different perspective than many of the other people many of the French scientists in particular, who were developing the study of electricity and magnetism, who believe entirely in action at a distance and who did not speculate about any kind of magnetic or electric fluid that was filling a space in between magnets or in between electrical charges. The most obvious deduction from this new fact, the one discovered by Ørsted, was that the action of a current on the magnet is not a push-pull kind of force, but a rotary force, and accordingly many minds were set to speculating on vortices and streams of ether whirling around the current, and Ørsted was one of those minds who was speculating in that way. But Ampere, by a combination of mathematical skill with experimental ingenuity, first proved that two electric currents act on one another, and then he analyzed this action into the resultant of a system of push and pull forces between the elementary parts of these currents. So you might remember the experiment that we did in lab earlier this semester, the force between two electrical currents. And Ampere was able to formulate that force in terms of a direct action at a distance without referring to a magnetic field. The formula of Ampere, however, is of extreme complexity as compared with Newton's law of gravitation, and many attempts have been made to resolve it into something of greater apparent simplicity. I have no wish to lead you into a discussion of any of these attempts to improve a mathematical formula. Let us turn to the independent method of investigation employed by Faraday and those researches in electricity and magnetism, which have made this institution one of the most venerable shrines of science. So what Maxwell is doing here now is he's recounting how Ampere was able to explain the forces between electrical currents in terms of complicated mathematical formulas that made no mention of a medium filling the space between those wires. But Faraday, Michael Faraday, is perhaps most notable for his conception of the magnetic field. And so Maxwell now is going to talk about how Michael Faraday developed and employed the notion of the magnetic field. No man ever more conscientiously and systematically labored to improve all his powers of mind than did Faraday from the very beginning of his scientific career. But whereas the general course of scientific method then consisted in the application of the ideas of mathematics and astronomy to each new investigation in turn, Faraday seems to have had no opportunity of acquiring a technical knowledge of mathematics, and his knowledge of astronomy was mainly derived from books. Faraday was not well trained in mathematics. Hence, though he had a profound respect for the great discovery of Newton, he regarded the attraction of gravitation as a sort of sacred mystery, which, as he was not an astronomer, he had no right to gainsay or to doubt, his duty being to believe it in the exact form in which it was delivered to him. Such a dead faith was not likely to lead him to explain new phenomena by means of direct attractions. Besides this, the treatises of Poisson and Ampere, the French scientists that study electricity and magnetism, are of so technical a form that to derive any assistance from them the student must have been thoroughly trained in mathematics, and it is very doubtful if such a training can be begun with advantage in mature years. Thus Faraday, with his penetrating intellect, his devotion to science, and his opportunities for experiments, was debarred from following the course of thought which had led to the achievements of the French philosophers, and was obliged to explain the phenomena to himself by means of a symbolism which he could understand, instead of adopting what had hitherto been the only tongue of the learned. This new symbolism consists of those lines of force extending themselves in every direction, from electrified and magnetic bodies which Faraday in his mind's eye saw as distinctly as the solid bodies from which they emanated. So Faraday came up with this pictorial way of understanding the interaction of magnets and the interaction of electrical charges, and that pictorial way was to draw lines of magnetic force and lines of electric field, or electric force, that later became known as magnetic fields and electric fields. The idea of lines of force and their exhibition by means of iron filings was nothing new. They had been observed repeatedly and investigated mathematically as an interesting curiosity of science. But let us hear Faraday himself as he introduces to his reader the method which in his hands became so powerful. Faraday writes, "It would be a voluntary and unnecessary abandonment of most valuable aid if an experimentalist who chooses to consider magnetic power as represented by lines of magnetic force were to deny himself the use of iron filings. By their employment he may make many conditions of the power, even in complicated cases, visible to the eye at once, may trace the varying direction of the lines of force and determine the relative polarity, may observe in which direction the power is increasing or diminishing, and in complex systems may determine the neutral points, or places where there is neither polarity nor power, even when they occur in the midst of powerful magnets. By their use, probable results may be seen at once, and many a valuable suggestion gained for future leading experiments." So in other words, Faraday is explaining how the idea of lines of magnetic force, or the existence of a magnetic field, is not only illuminating in understanding complicated magnetic configurations, but it also can lead one to new discoveries